Assalamualaikum and a very good day everyone. Today we will explain about our project on utilization of watermelon rind for the production of bioethanol. Before that, let me introduce myself. My name is Nur Hanisah binti Zulkifli and I'm here today with my two amazing groupmates, Nur Fatina Diha binti Azizul and Ain Shahira Izzati binti Nur Izan. Have you ever wondered what happened to watermelon rind after we enjoy the juicy of the watermelon? Most of the time it just ends up as a waste. But today we will tell you that the waste can be turned into something valuable like bioethanol. Bioethanol derived from the renewable resources has attracted significant attention as a sustainable alternative to partially substitute fossil fuels in the transportation sector. Bioethanol is in fact a cheap source of energy and can help in clean environment management. Among these resources, watermelon rind waste, an abundant byproduct of the agriculture industry with a high cellulose content, offers significant potential as a feedstock for the bioethanol production. Globally, an estimated 540,000 metric tons of the watermelon rind are discarded as agricultural waste each year. If the biomass can be effectively utilized as a source of ethanol production, it will not only provide an environmental-friendly waste disposal solution but also offer additional economic benefit to the farmer. However, traditional bioethanol production process from lignocellulosic biomass waste often face challenges such as high energy consumption, low yields, and elevated carbon footprint, primarily due to inefficient pretreatment method and energy-intensive distillation step.
Next, I will continue with feedstock selection. For the first one is greenhouse gases. Greenhouse gases or GHG emission occur at various stages throughout the life cycle of watermelon processing. The first stage involves the collection and transportation of watermelon rinds from farms to processing plants, which contributes to carbon emission due to fuel consumption during transit. Following this, the fermentation and distillation processes convert watermelon rinds into bioethanol, utilizing heat and energy, both of which can further increases GHG emission, if not managed efficiently. Finally, effective waste management is crucial to handling leftover materials properly, as improper disposal can lead to additional emission. By addressing these stages, we can better understand and mitigate the overall carbon footprint associated with watermelon waste conversion into bioethanol. Next is lower carbon impact. Using agriculture waste is a great way to reduce our carbon impact and benefit the environment. When we manage agriculture byproducts effectively, we can prevent them from ending up in landfill, which help reduce greenhouse gas emission. For example, instead of throwing away leftover material from crops, we can turn them into valuable resources like biofuel, compost, or even ingredient for food product. This not only minimize waste but also support sustainability practices. By finding ways to use agriculture waste, we can contribute to a healthy planet and create a circular economy that reduces our overall carbon footprint. The last one is life cycle assessment or LCA. LCA is a method we use to evaluate the environmental impact of a product throughout its entire life, from start to finish. It looks at several stages, including the extraction of raw material, the production processes, transportation, usage, and what happened at the end of the products like disposal or recycling. LCA helps us understand various environmental factors such as carbon emission, water usage, and energy consumption. By gathering and analyzing data at each of these stages, we can identify the strengths and weaknesses of a product environmental impact. This assessment is essential for a business and policy makers because it guides them in making informed decisions that minimize negative effect on the environment and promote sustainable practices. Overall, LCA is a valuable tool for achieving sustainability in our product and process. Another feedstock selection is resources use analysis. Resource use in bioethanol production from watermelon rinds include water, energy, and chemical inputs. Water is used in several stages of process, including pretreatment, fermentation, and distillation. However, because watermelon rinds are an agriculture waste product, they do not require irrigation like food crops such as corn or sugarcane, so making them more water efficient. Energy is also an important factor as both fermentation and distillation require heat and electricity. If fossil fuels are used to provide this energy, the process becomes less sustainable. However, using renewable energy sources like solar power or biomass can reduce the environmental impact. Additionally, enzyme and acid are sometimes used to break down the watermelon rinds before fermentation. If these chemicals are not managed properly, they can lead to pollution. Therefore, careful resources management is essential to ensure the process remains environmentally friendly and sustainable. The last one for feedstock selection is environmental impact. By using watermelon rinds, it's more eco-friendly to make bioethanol because it can reduce agriculture waste in landfill. It also prevents organic waste from ending up in landfill where it can release harmful methane gas. Next, the leftover material from the fermentation process can be reused as animal feed, compost, or for making biogas to generate energy. But if not handled properly, the leftover waste or water can be soil and water pollution. Proper waste treatment is important to keep the environment safe. This method supports sustainable development and cleaner environment.
Now I want to explain about how bioethanol is made from watermelon waste using fermentation. The process helps to reduce waste and produce a useful renewable energy, which is ethanol. Watermelon waste is collected and focused on the juicy part of the fruit. The seeds and rind are removed. The juice is then filtered to get a clean liquid. And that juice contains natural sugars like glucose and fructose, which yeast will turn into ethanol. Before the fermentation process, the pH of the juice is adjusted to about 4.5. Then, yeast is added. The type of the yeast is used, which is also used in the bread and beer making. Step 3. Anaerobic fermentation process. The mixture is placed in an airtight containers to maintain anaerobic condition, also to trap any carbon dioxide produced. It stays around 30 degrees Celsius for 2 or 3 days. During this time, the yeast use the sugar and produce ethanol and carbon dioxide. After the fermentation, ethanol is separated from the mixture using distillation. This process gives bioethanol about 7.4% alcohol by volume. The ethanol yield is closely related to the initial sugar content of the watermelon juice. The process is economically and environmentally beneficial as it utilizes the agricultural waste, reducing disposal issue while generating renewable energy.
Next, I will continue with sustainability. The first one is food security. One of the main concerns with bioethanol production is how it affects food security. Usually, bioethanol is made from food crops like corn, sugarcane, or wheat. It can reduce the amount of food available and cause food prices to go up. This is because the same crops are being used for fuel instead of feeding people. However, using agricultural waste like watermelon rinds is a better option. These materials are not used for food, so they don't compare with the food supply. This makes bioethanol production more sustainable, also can help to reduce waste. Another one is energy security. Bioethanol is a renewable fuel that can be made locally, unlike fossil fuel like oil and gas, which often have to be imported from other countries. This makes it helpful for improving energy security because countries can produce their own fuel. However, bioethanol doesn't have as much energy as gasoline, so more of it is needed to get the same amount of power. Luckily, newer technologies are improving how we make bioethanol, especially when using waste materials like watermelon rinds. This improvement make it more efficient and better for the environment. Bioethanol can also work well with other renewable energy sources like solar. Since solar can be unreliable when the sun isn't shining, bioethanol can be used as steady as backup fuel when needed.
So now, let's take a closer look on how recent technological advancement and process improvement can help to reduce the carbon footprint of bioethanol production through fermentation. Let's begin with the first technological advancement, deep eutectic solvent for biomass pretreatment. Deep eutectic solvent (DS) have gained significant attention as an innovative and sustainable alternative to conventional solvent for biomass pretreatment. Unlike traditional solvent, DS are tenable, non-flammable, chemically and thermally stable, and possess no vapor pressure and a variable viscosity. These characteristics make them highly suitable for bioethanol production, particularly in breaking down lignocellulosic biomass. DS are liquid mixture typically composed of a hydrogen bond acceptor (HBA) and hydrogen bond donor (HBD). Their low melting point and ability to dissolve a wide range of biomaterial make them effective for biomass pretreatment. The development of DS-based pretreatment method aims to create more eco-friendly and cost-effective alternative to traditional chemical solvents, such as ionic liquid. Lignocellulosic biomass, such as watermelon rind waste, consists primarily of cellulose, hemicellulose, and lignin, with lignin acting as the main structural barrier that hinders enzymatic access to cellulose. Deep eutectic solvent function by breaking the hydrogen bond between lignin, hemicellulose, and cellulose, selectively dissolving lignin and hemicellulose while preserving cellulose. This process enhances the accessibility of cellulose for enzymatic hydrolysis, as the removal of lignin exposes more cellulose fibers, increasing surface area and improving enzyme binding, which leads to higher glucose yield. DS pretreatment operates under mild conditions, typically between 16 to 120 degrees at atmospheric pressure. This significantly reduces energy consumption, making the process more cost-effective and environmentally sustainable by minimizing harsh chemical usage and high-temperature processing. DS pretreatment also lowers the carbon footprint of bioethanol production. To evaluate the effectiveness of different pretreatment methods for bioethanol production from watermelon rind waste, various studies have been conducted, including those utilizing conventional approaches such as dilute acid hydrolysis. One such study found that pre-treating WRW with 2.5% sulfuric acid at 90 degrees for 30 minutes yield the highest reduced sugar concentration of 1.04 plus minus 0.02 gram per liter. Following fermentation with Saccharomyces cerevisiae, the resulting bioethanol yield was recorded at 0.13 plus minus 0.017 milligram per liter. In contrast, the application of deep eutectic solvent in combination with ultrasonification has demonstrated a substantial improvement in bioethanol production. A study employing this method reported a bioethanol yield ranging from 0.276 to 0.458 gram per gram of raw WRW, achieving a fermentation efficiency between 54.12% and 89.80%. Moving on to the second investment, now we will focus on the fermentation with immobilization cell system. One of the strategies used for improving the fermentation is the immobilization cell technology that allow the implementation of continuous processes with higher yield and productivities and with increased cell concentration. Immobilized cell fermentation enhance bioethanol production by keeping microorganisms fixed in a specific location rather than fully suspended in a fermentation medium. As a result, shorter residence time and smaller reactor size can be employed. Additional benefits include enhanced ethanol yield, prolonged cell stability, greater tolerance to higher substrate concentration, reduced product inhibition, and easier product recovery. These advantages may contribute to lower energy consumption, reduced process costs, extended cell reuse in batch system, and the feasibility of continuous fermentation while mitigating risks associated with high cell densities. The effectiveness of immobilized cell depends on several factors, including the characteristics of the carrier material such as pore size, particle size, water content, and hydrophilicity. Common immobilization technique involves cell entrappment in gel like carrageenan and calcium alginate. Other methods utilize passive adhesion to solid surfaces such as glass bead and stainless steel wire sphere. Additionally, various lignocellulosic material, including orange peel, wooden chips or blocks, sorghum bagasse, rice husk, sugarcane, and wheat starch granule, have been explored as microbial supports. Lignocellulosic biomass, which is pre-treated to release fermentable sugar or other sugar-rich feedstock, are introduced into the system. Immobilized cell convert sugar into ethanol and carbon dioxide through metabolic pathway such as glycolysis and fermentation. Since cells remain concentrated in the system, ethanol production occurs at faster rate compared to traditional suspended cell fermentation. A key advantage of immobilized cell fermentation is the ability to support continuous processing, where fresh substrate is added while ethanol is simultaneously removed, improving production efficiency. If operated in batch mode, the cells can be reused for multiple fermentation cycles, reducing cell loss and lowering overall production costs. After fermentation, ethanol is separated and purified through techniques such as membrane distillation. The immobilized cells remain intact, allowing for their use in subsequent cycles. However, immobilized cell systems have some limitations. Calcium alginate-based entrapment system, for example, can be unstable in the presence of phosphate and may degrade due to carbon dioxide release during fermentation. In adhesion-based method, cells bind to the carrier surface through electrostatic interaction or covalent bonding, but challenges including limited biomass loading and the risk of the cell detachment, which affect long-term operational stability. The final technological advancement and process improvement is membrane bioreactor system, which is MBR. Membrane bioreactor system (MBR) with different configuration have been implemented for simultaneous separation of fermented product using per-evaporation technique. Per-evaporation is well known as an efficient separation method for separation of ethanol, water isotropic mixture compared to distillation. High alcohol water selectivities are critical to the energy efficiency of per-evaporation. There are some reports in the literature discussing about continuous ethanol production by per-evaporation using different culture, membrane, and configuration. Studies have indicated that integrating fermentation with per-evaporation using a syndicate membrane which selectively separate ethanol can achieve an 85% volume over volume ethanol concentration. Additionally, this process has been shown to enhance the average glucose consumption rate by approximately 20%. The use of MBR can significantly lower the amount of the water needed during bioethanol production. Conventional distillation is an energy-intensive process consuming approximately 4 gallons of cooling water for every gallon of ethanol produced. This represents a significant portion of the total energy usage in ethanol plant. By utilizing a membrane to separate ethanol, MBR system limit the exposure of fermentation broth to environment, thus decreasing risk associated with contamination. This controlled environment is crucial for maintaining yeast productivity and improving process reliability. Furthermore, the high cell density operation of MBR leads to improved biomass utilization, reducing the amount of residual biomass waste. Additionally, the system allows for the recovery of valuable byproducts such as lignin or unfermented sugar, which can be repurposed for bio-based material or energy production, enhancing the circular economy of bioethanol production. MBR can achieve high selectivity for ethanol over water during the separation process, which enhances the efficiency of ethanol recovery. By optimizing fermentation and ethanol recovery, MBR system lower the overall carbon dioxide emission associated with production. The reduced energy-intensive distillation can improve waste management, further decrease the carbon footprint. So here let's take a look at the flowchart on how bioethanol is produced from watermelon rind waste. First of all, the process begins with watermelon rind waste and abandoned agricultural byproduct rich in lignocellulose. This waste is processed into lignocellulosic biomass, which contains three main components, which is lignin, cellulose, and hemicellulose. All the three components are crucial for bioethanol production. Next, the biomass undergoes DS pretreatment, where deep eutectic solvents are used to break down the complex structure of the biomass and help separate the lignin. After pretreatment, we obtain a more accessible form of biomass with lignin removed and cellulose and hemicellulose available for further combustion. The pretreated biomass then goes through enzymatic hydrolysis, where enzymes break down the cellulose into fermentable sugar. These sugars are then fermented using an immobilized cell system and membrane bioreactor (MBR) system, technologies that enhance the efficiency of ethanol production. Following fermentation, ethanol is separated and recovered through an ethanol recovery system. The end product is bioethanol, a renewable and eco-friendly fuel that can help reduce our reliance on fossil fuels. Next, we move to the next part, which is recommendation for scaling up bioethanol production approach using watermelon rind waste. Scaling up watermelon rind waste utilization for bioethanol production provides a sustainable solution for both waste management and renewable energy generation. Diverting at least 40% of food waste from landfill reduces methane emission, a major contributor to global warming. Utilizing biogas from fermentation waste to power pretreatment and membrane bioreactor (MBR) operation enhance energy efficiency and lowers reliance on fossil fuels. Since biogas originates from biomass, it forms part of natural carbon cycle, creating a closed-loop system where emissions are minimized and continuously recovered. Conducting a life cycle assessment, LCA ensures bioethanol production remains a low-carbon solution by evaluating environmental impact across the entire supply chain, including land use, water consumption, and transportation emissions. Implementing cogeneration system for heat and power further reduce fossil fuels dependence, improving overall efficiency. Integrating recycle and cogeneration system has been shown to lower environmental impact by up to 3.46%. Monitoring microbial activities and substrate utilization is also crucial to preventing productivity losses. A comprehensive approach ensures bioethanol production remains truly sustainable with minimal carbon footprint.
Conclusion, producing bioethanol from watermelon rind waste offers a sustainable and efficient solution for waste to energy conversion. By utilizing the natural sugar in watermelon rind, the process eliminates the needs for expensive pretreatments, making it both cost-effective and eco-friendly. Emerging technology like deep eutectic solvent and membrane system further improve the process efficiency. Additionally, this method supports a circular economy by turning valuable byproducts such as compost and biogas. Overall, bioethanol production from watermelon rind presents a promising approach to addressing energy and waste management challenge in a sustainable way.